Hello everybody, and welcome to the Front Room. I'm your host, Nathan Rigoni. In this series, we're going to cover some of the basics of artificial intelligence and machine learning. The point of this series is to introduce most of you to the concepts that make up the basis of many of the technologies that exist in AI today. Break those technologies down into their components, and I'll try to explain from the beginning how we got here, what we use, and why. This should also help you understand what the concepts are, the limitations of AI, and what the future may hold for this technology in its use cases and industry. In each episode, we will choose one topic and we will break it down. I'm hoping to keep the episodes to less than 15 minutes. I hope that these episodes help, and I hope that you enjoy them. In this episode, we're going to cover NLP applications, and we're going to cover some of the cooler ways that we can use natural language processing in order to understand some of the documents that we typically have in our workplace or in the internet, and how we can do some cool things by processing words. Let's dive in. One of the very first models that I created was using natural language processing. And this is actually something that really intrigued me in the beginning, and it's kind of what got me into AI. And the first model that I built was a classifier, and it was essentially doing some data entry and labeling services for my job. But the thing that I had to figure out, and I figured out over time as I was being birthed into this, is that there are many, many, many different ways to deal with language. And one of the things that we actually have done as humans is we've created an entire field called linguistics that study and analyze and basically write the rules for how language actually works. It's a good thing that that actually happened, because that's kind of one of the guiding factors for how we do NLP and how we started to break down NLP and make it successful in AI. It's part of what made language processing possible. The classifier turned out to be pretty successful, but one of the major things I had to learn was how to tokenize. And once I had learned that, I needed to learn how did things like words get their meaning. And so today I kind of want to talk about a historical application of NLP and how it's used today, and how it has birthed some methods used today to analyze documents. That application is Word2Vec. Word2Vec was one of the original ML models that came out to help with natural language processing. And what it did was essentially, after you tokenized each word in it's called a corpus, which is all the words in your data set. After you tokenized each word in your corpus, what it would do is it would work like an autoencoder. If you listen to the latent space or hidden state episode, it would work like an autoencoder to look at all of the words and then essentially try to organize them so that words that were related would be near each other. This was a huge breakthrough when they first discovered it, and everybody started using Word2Vec. In fact, I can still see in my mind the key graphic that they used, where they would say the word king minus the word crown equals man. And inside that hidden state, after you train the Word2Vec model, that was true. You could actually take the word for king and take the vector in that hidden state, and you could take and subtract the vector for the word crown, and you would get the vector for the word man. And this was amazing. This was fantastic. This is what led us to do things like topic analysis later. But it also led us to do things like I did with it, which was build a classifier. You could then actually see sort of what words were in documents, and then be able to parse those words and look for specific combinations of words in order to be able to label the documents according to some labeling standard. And this allowed us to automate a lot of processes in labeling instead of relying mainly on data entry. But this all goes back to the basis in linguistics for like why does word-to-vec work? And the key mechanism for word-to-vec is actually based in a rule that is in linguistics. And it's that every word is actually defined by the words that are around it. And so the process for getting that hidden state or training the model for word-to-vec was to take and you would blank out a word and you would only look at the words surrounding the blank, and then you would train the model to guess the word that was in the blank. And the better that it got at doing that, it would relate the words, all of the words that were like each other or that could fit into a particular blank because the words around that blank were very similar. It would be able to relate all the words together and essentially learn their meaning. That principle, again, that principle comes from linguistics. Now that we've progressed to LLMs, there are even more principles that are coming out, and this is why NLP is one of my favorite things that has come out of AI. Some of the things that happen with LLMs when we are starting to look at what is hallucination versus what is the truth, there are philosophical documentation and papers that exist that actually talk about language and its uses and how the perspective that we have on language changes things for how we should interpret it. Let me give you an example. If I tell you that the moon is made of cheese, that's obviously not factually correct in the real world. But if I told you that I was reading a line from a book where the moon was actually made of cheese, and it was a story about like a cat and a mouse, that would be factually correct. So that it's not that a statement holds its own factual correctness by itself. That's not what is actually contained within language. And this is actually something that was shown by a guy named Ludwig Wittgenstein in his philosophical paper, which I will link in the description. It's essentially the context under which it's decoded. This also is a reference that goes back to an even older paper, and I don't want to get too technically deep here because we're just talking about natural language, but this goes back to the paper that C.E. Shannon wrote that revolutionized computing when he started talking about and writing the theory of information. He published his information theory paper. And in the beginning of the information theory paper, he basically breaks out that all information has to be broken down into two things. There are messages that are sent, and then there is this thing called context or assumed context, under which the message has to be decoded. The thing he really wanted to study was if you made the assumption that given two people had the same assumed context, what is the minimal message that you have to send in order to get a definitive answer from one place to another? And this is sort of what breaks down into bits theory. An anecdote here, right? Let's say that I am in a closet and you are in another room, and we have essentially a telecommunication device where I can press it down and it'll give you a beep, or I can leave it open and there's no beep. So this would represent a bit, a 0 or a 1. And what I have to do is I have to roll a die, and then I have to somehow send you a message in bits to tell you what I rolled. Now, I could just crank out 6 beeps, right? But now we're talking 6 bits, right, to tell you what I rolled. Or we could agree on some previously assumed context beyond the fact that you know that I'm going to roll a die, and that's the message that you're going to receive. And you could know, because I told you beforehand, that the first bit that I'm going to send is to tell you that that I rolled either an even number with a 0 or I rolled an odd number with a 1. Now, given that I go all of the odd numbers and all of the even numbers on the first bit, and I cut all of the information in half, I can now, with less bits, send you the rest of the information. So it's not going to be the full 6 beeps. I need less beeps than that. So I can use less bits. This was essentially what he was trying to figure out. It's like, how can we boil down the least amount of information as far as transmission in order to transmit the least amount, but still send the message? And it comes down to, like I said, I want to repeat myself here. It comes down to assumed context. What is the assumed context? Now, this is where a lot of people go wrong with large language models, and we'll dig into that a bit later. But they don't think about the assumed context with a large language model. A large language model hasn't lived in this world like we have. It hasn't grown up. It essentially doesn't know how to see, and a lot of the things that we assume that it knows or assume that it functions with, it doesn't. It hasn't experienced that. So when you talk to a large language model, it's always best to be verbose and specific about what you're talking about first to introduce the topic, and then ask the question that you want to ask. And that's why RAG works, retrieval augmented generation. But we'll get into all of that later when we start talking about large language models. The thing I want to reiterate here is that the basis of natural language processing comes down to tokenization, and it comes down to the things that we knew from linguistics, that words and tokens and their associations with the words and tokens next to them are what define them. These are the things that help us build the language models that we build today. I'd like to thank you for listening, and I hope you enjoyed this episode. You've been listening to The Front Room. The Front Room is written, recorded, and produced by me, Nathan Rigoni. If you'd like to know more about what our company does and what it could possibly do for you, you can reach us at nathan.rigoni@phronesis-analytics.com. We'd like to thank you for listening, and have a good day.